Extra high-voltage gas-insulated switchgear operates at energies requiring precise verification. Commissioning is the process of confirming every safety and performance parameter. This dashboard outlines the complete 18-module commissioning electrical grid program. We begin with Module 1, GIS and Switchgear, the foundational starting point for the physical grid interface. Traceability is the prerequisite for a valid record. An entry is void if the result, instrument certificate, and witness decision cannot be traced to an approved source. This flow diagram outlines the required chain of custody for every test. An authorized reference dictates the test procedure, which is executed with calibrated instruments, yielding a measured value and finalizing in a verified record approved by a witness. When project specifications, manufacturer guidelines, and international standards like IEC or IEEE differ, the most stringent requirement governs the test parameters. A recorded test value is a failure if the physical safety boundary and documentation trail are incomplete. To execute these procedures in the physical environment, commissioning engineers rely on a specific hardware inventory. The 5 kV DC insulation resistance tester proves the integrity of phase-to-ground and phase-to-phase insulation. The 100 amp DC micro-ohm meter measures millivolt drops to validate low-resistance current paths across main contacts. The circuit breaker analyzer maps mechanical operating times down to the millisecond, and the portable UHF monitor detects partial discharge emissions that indicate microscopic insulation flaws. These instruments cannot be connected to the switchgear until the lockout-tagout boundary is confirmed. This requires barricading the work area, establishing physical safety tagging, and verifying the absence of voltage directly with the switching authority. Physical execution of GIS circuit breaker tests begins only when equipment is physically isolated from the grid and its safety state is verified. Testing begins with static integrity to confirm the health of the insulation and the main current paths before verifying dynamic operation. Looking at this schematic for the phase-to-ground insulation test, the earthing termination is removed only on the tested phase. The tester injects 5 kV DC on phase R for 1 minute, keeping phases Y and B grounded, needing a stable resistance exceeding 100 megaohms. Because GIS components retain a significant capacitive charge, the circuit must be fully discharged using approved rods before altering any connections for the next phase. Moving to the contact resistance test, this schematic shows the setup designed to push high current directly across the closed main contacts. The instrument injects 100 amps DC across the path, recording the voltage drop to calculate exact resistance in microohms. Achieving a contact resistance below 300 microohms across all 3 phases confirms the breaker can safely carry grid-level current without overheating. Once static integrity is verified, we test the breaker's dynamic mechanical operation and control logic. This diagram shows how the circuit breaker analyzer maps its channels to the close coil, trip coil, and main phase timing points to measure millisecond response times. The operating time for both open and close commands must register under 20 milliseconds, with simultaneity across all poles to prevent phase imbalances. This schematic details the anti-pump relay circuit, preventing continuous cycling during a fault. We simulate a fault with a sustained close command while a trip signal is active. The 52Y relay energizes, holding the closed circuit open even if the operator command remains active. Validating this crucial physical contact block prevents catastrophic mechanical self-destruction of the switchgear equipment during severe grid emergencies. The final physical stress tests push the equipment to its operational voltage limits using very low-frequency injection, while monitoring for microscopic flaws using UHF partial-discharge detection. This diagram illustrates the VLF high-voltage test procedure on 13.8 kV switchgear. A potential of 3 times the rated operating voltage is applied, with the circuit breaker in both the on and off positions. During the high-voltage injection, leakage current must remain below limits, without any flashovers or abnormal acoustic noise. Beyond hardware, we validate system-wide protection logic. The pole-discrepancy scheme protects the entire power grid if a single massive breaker phase fails to operate in sync with the others. This schematic for the Stage 1 test logic shows the removal of the close command for a single phase. The scheme must detect this discrepancy and trip the local breaker within the approved time delay. If the local trip fails, this Stage 2 schematic outlines the escalation path. The system triggers the 86PD2 lockout relay to initiate a full busbar clear and remote end trip. Verifying these cascading lockouts ensures a localized mechanical failure is isolated before propagating into grid-wide instability. In FIOB execution, anomalies and failed readings occur regularly. Any missing record, fluctuating reading, or failed timing trace creates an open punch item that halts the release of the equipment. If a contact resistance reading is unstable, the troubleshooting protocol dictates a physical investigation into dirty test terminals, induced voltages, or damaged lead clamps. If an interlock, like the anti-pump relay, fails to block a reclose, the contacts will continuously cycle and strike against each other under fault conditions. The commissioning engineer ensures system reliability by rigorously diagnosing and documenting these deviations. The final requirement before releasing a bay is equipment normalization. Leaving a single temporary test link or bypass in place compromises the active grid. Normalization requires removing all test leads, restoring earthing to approved switching states, and reinstalling all panel covers and physical barriers. Only after this restoration is verified does the handover from the commissioning authority to operations occur, finalizing the approved energization permit. When the final trip is closed and the system receives live high voltage, the uncompromising adherence to this governance workflow keeps the grid active and the personnel safe.